So good morning. We'll start new chapter, that is chapter number 9, image compression standards. So in last chapter we have studied about the DCT and wavelet transform in detail. Now this DCT and wavelet transform is used as a transform in compression technique. Okay, so in this chapter we'll study the image compression standards, that is Jpeg. Okay, so this Jpeg standard was developed by Joint Photographic Expert Group. Okay, Jpeg was formally accepted as an international standard in 1992. So this is the standard for still image compression. Okay, not video compression. Video compression, there is another standard, that is MPEG and H.261 or H. series. Okay, so this Jpeg standard is for lossy as well as lossless. Okay, so Jpeg is lossy image compression method. It employs transform coding method by using DCT. Okay, and an image, you know, that is a function, okay, of I and j, f of I comma j. Okay, where I and j are nothing but the spatial coordinates of that image. Okay, and the value at that coordinate is nothing but the intensity of that image. Okay, so this image is represented in spatial domain. Now by taking the transform of that image, okay, we are representing that image in a frequency domain. So this frequency domain, we call that as a spatial frequency domain. Okay, so f of uv is the spatial frequency domain representation of f of ij image. So by using DCT we can represent that image in a spatial domain. Okay, now there are three main observations in case of Jpeg. Okay, what are those observations? So that we'll study first, and then so this Jpeg committee has taken the advantage of those observations to do the compression. Okay, so the effectiveness of DCT transform coding method in Jpeg relies on these three main observations. Observation number 1 is useful image content change relatively slowly, okay, across the image. That is, it is unusual for intensity values to vary widely several times in small area, for example within an 8x8 image block. Means if you consider the entire image, okay, if you consider the small block, most of the pixel intensities in that small blocks are same. So change of the pixel intensity is less. Okay, so that is the meaning of this first observation. So useful image content change relatively slowly. You see that if you consider, so for example, if you have an image of 512 by 512 image, out of that if you consider a block of 8x8, okay, the pixel intensities of this 8x8 block, okay, generally have same intensity values. Okay, generally have same intensity values, means rate of change of pixel intensity is less, so spatial frequency is less. Okay, so this is first observation. Okay, so much of the information in image is repeated, hence there is a spatial redundancy. What is by spatial redundancy? Means suppose for example if you have an image of 512 by 512, means there are 512 rows and 512 columns. Okay, so this is first row, second row. Okay, this is the 512 row. Okay, this is your first column, this is second column, and this is the 512th column. Okay, 512th column, this is 512th rows. Okay, now the intersection of all those is nothing but the pixel location. Okay, so if you consider a block of 8x8 anywhere, okay, most of the pixel intensities within that block is same. Okay, so basically see that these pixel intensities in this 8 by 8 block are same, so we can call that it is a redundant information. And since image is represented in spatial domain, so that's why it is called as a spatial redundancy. Okay, now there are two important things in compression. One is to reduce the redundancy, okay, and another one is to reduce the irrelevancy. Okay, the information which is not relevant is suppressed, and the information which is redundant is also suppressed. Okay, so see that if you consider any small area of the image, okay, it contains the same pixel intensity, so the rate of change of pixel intensity is less, means there is a what kind of frequency? Low spatial frequency. And then if you consider the pixel intensity, it is almost same, so there is a spatial redundancy. So if you reduce that spatial redundancy, okay, compression will be achieved better. Okay, so much of the information in image is repeated, that is spatial redundancy is there. Second observation is that, okay, psychophysical experiments suggest that humans are much likely to notice loss of very high spatial frequency component than the loss of lower frequency component. Okay. What is the meaning of this one? Means suppose for example you have two images. Okay, image A is there and image B is there. Okay, now this image A okay, and image B is there, which contains several vertical lines. Okay, now in image A, how many vertical strips are there? 3. Okay, this is your first vertical strip. Okay, this is second one, and then this is third one. Okay, whereas here there are n number of vertical strips. Now suppose for example if I remove this vertical strip from this image, okay, after that what will happen? My image, so for example this has been removed, this has made like this, so my image will look like this way. Now here, so for example if I remove one vertical line out of this image, okay, what I'll get? Is it possible to notice the change between this image and this image? This is not possible. Okay, so that is what the second observation is that. So now where basically what is the frequency of this image? Spatial frequency of A image and spatial frequency of B image. Spatial frequency of A image is low and spatial frequency of B image is high. So if we lose some information in high frequency, our human eye does not detect that one. But if you lose low frequency, okay, we can easily detect that one, and that advantage is taken in case of Jpeg. Okay, see that first one is spatial redundancy is reduced. Second one is even if there is a loss of high frequency information, our human eye does not detect that loss. Okay, so this is second observation. So all those observations are useful in Jpeg. Okay, so the spatial redundancy can be reduced by largely reducing the high spatial frequency content. Okay, now observation number 3 is visual acuity, that is accuracy in distinguishing closely spaced lines is much greater for gray or black and white than the color. Okay, we can See that visual means accuracy in distinguishing closely spaced lines is much greater in grayscale, okay, as compared to color, okay, and that's why in Jpeg or even in MPEG also, okay, we take the subsampling as 4:2:0 in Jpeg as well as in MPEG, okay. So these are the three reasons or three observations in Jpeg image compression. Now see that this is a block diagram of Jpeg image compression. First one is your original image is, okay, converted into a YIQ or YUV model of color space if it is color image. If it is grayscale image, there is no need of converting that one. After that, the whole image is divided into 8x8 block. Okay, why 8x8 block? Okay, after that, on each 8x8 block, DCT is applied. Okay, first we should answer why they have selected 8x8. Redundancy, okay, means basically in the small area of the image there is lot of redundancy. Okay, now is it not possible to consider the 16x16? Would have got better result now? Then why 8x8 is selected? See, the whole image is divided into 8x8 non-overlapping areas, and then for each 8x8, okay, part of that image, DCT is taken, two-dimensional DCT is taken. Okay, what you will get after taking the DCT? So for example, here you have this 8x8 part of the image. If you take the DCT of this one, okay, you'll get the DCT representation of the image. Means what exactly you get? You are representing that spatial domain information into spatial frequency domain information. So spatial frequency means there must be some low frequency, there must be some high frequency. Okay, so you are representing that one into a spatial frequency. For what purpose you are representing that one? Is it not, first thing is that, okay, for decorrelating the data. Now how you are decorrelating that data? Okay, means there was more correlation in the original data? Yes or no? See that when you are considering the small area of the image, okay, the neighboring pixels are having similar intensity, means there is more correlation between the neighboring pixels. Okay, so if you consider the 8x8 block, most of the pixels are having same intensity, so there is more correlation. Now you are decorrelating that one. How you are decorrelating that one? You are representing that spatial domain information into frequency domain, means you are, okay, representing that what is the low frequency information, what is the high frequency, means AC 1 component, AC 2 component, 2 up to AC 63 component. So definitely you are representing that what is the DC component, what is the AC 1 up to AC 64 if you are considering the 8x8. Okay, now in that basically you will get maximum value of DC component and less value of AC component. Okay, means now if you consider the spatial frequency representation of this image, okay, is there any correlation between the neighboring coefficients? So for example, here you have all those 8x8 area, okay, or all those 8x8 pixels. If you, okay, if this intensity is 200 of all those 8x8, if you represent this one into a DFT, if you take the DFT, DCT, two-dimensional DCT of this one, okay, you will get how many, see how many pixels are there? There are 64 pixels, okay, and then your size of that one is 8x8, your output of this one will be also 8x8, okay, and then it will be 8x8 and number of DCT coefficients will be also equal to 8 by 8. Out of that, okay, if you consider this as a U, this as a V, see in original form it was I comma Z. So this was your image f of I comma Z. Now after taking the discrete Fourier transform, discrete cosine transform of this block, it will be represented into another domain, that is nothing but the spatial frequency domain, and this coordinates will be U and V. Now earlier the coordinates were I and Z, so these are the frequency coordinates. So when U equal to 0, V is equal to 0, so this block or this value is nothing but the DC value. Okay, as U and V goes on increasing, see for this side V will goes on increasing, so this is the 7th value if you start from 0th, and then for U, if it is starting from 0th, this will be 7th value. As it goes on increasing, okay, frequency will also goes on increasing. Earlier all those pixels were having same intensity. Now after taking the DCT, see that if all the pixels are having same intensity, the rate of change of pixel intensity will be less, and if the rate of change of pixel intensity is less, we say that it is a low frequency area, means there is lot of low frequency information, and you know that DC value is nothing but low frequency. Okay, so here you'll get the maximum coefficient value, and since the high frequency value is less, so your coefficient, high frequency coefficient will be less. Now earlier here, if you consider the neighboring pixels, all those pixels were having similar value, that's why there was more correlation between the neighboring pixels. But after taking the DCT of this one, two-dimensional DCT, you got maximum value of this DC component and then minimum value of all those high frequency component. So you have decorrelated that data, means there is no correlation between this one, this one, this one, this one and this one. But in earlier case, there was lot of or high correlation between the neighboring pixel. Now what happens basically after decorrelating the data? You get maximum value of this one and minimum value of this one. See, what is our second observation? Our second observation is that, okay, human eyes are more sensitive to the low frequency and are less sensitive to the high frequency. So if you discard the high frequency component, human eyes will not detect that change easily. So if you discard the high frequency component from this one, and if you transmit only the low frequency component, compression can be achieved. Otherwise earlier how many pixels would have been transmitted? 8 by 8 in this one. Here how many? Very few. Okay, so compression can be achieved. Okay, so here after this one, dividing this original image into 8 by 8, okay, you are taking the DCT of each block. Now question is that why 8 by 8 size is selected? Why not 4 by 4, or why not 16 by 16, or why not 20 by 20? So definitely see that if you consider the 16 by 16 image, okay, compression will achieve, okay, it will be more, okay, but as the size of that matrix increases, the computational complexity in case of DCT also increases. Okay, so this Jpeg committee has agreed that this 8 by 8 is the optimum size of the block. Okay, 8 by 8 is the optimum size of the block. Okay, if you increase the size of that block, computational complexity will increase. Okay, now after that quantization step is there. Okay, so see that what you have done, basically spatial domain information is represented into frequency domain. After that you are quantizing the spatial frequency. Okay, quantization for what purpose? See, what is the purpose of quantization? Yes, to make signal discrete in amplitude. Okay, what is the advantage of that one? Okay, we have made signal indiscrete in amplitude. What is the advantage of that one? Okay, okay, fixed number of levels. Let me ask you whether number of levels will be decreased after quantization or it will be increased. After quantization, number of levels, okay, will decrease or will increase. See that quantization, what do you do with quantization? Means basically, suppose for example, if you have the intensity ranging from this one to this one, what you are doing? You are making the steps such that, okay, this part will be represented by some value, this part will be represented by some value, this part will be represented by some value, and so on. Means you are grouping all those pixel intensities here, okay, into one value, then this one into another value, this one to another value, okay, so that number of levels will be decreased. Okay, so if you reduce the number of levels, okay, definitely number of bits required will be also reduced. Okay, so now here, see, since you are grouping the pixel intensities together, okay, from certain threshold level, okay, so definitely for this level and this level you are calling it as only one level. From this level and this level you are calling second level, then third one, and so on. Means, okay, here you are losing some information. Okay, so quantization is a step of lossy operation. Okay, after quantization, okay, there are two encoding techniques used first. Okay, one is DPCM and another one is RLC. Okay, DPCM is used for DC coefficient. See that here in this case, when you take the DCT of the image, okay, you have what kind of components? DC component as well as AC component. After that, what you have done? Those components are quantized. Okay, means what will happen? So for example, if there is a less value of high frequency component, they after quantization, what will happen with those less value? It will be approximated to 0. Okay, so most of the AC high frequency components will be 0, no? Only low frequency component will be having the significant value. Okay, after quantization you are going to map it with the 0. After that, okay, there are two coding techniques which are used. Okay, one is DC and another one is AC. But see that, so for example, suppose for example this 8 by 8 block, okay, after taking the DCT of this 8 by 8 block, you got 8 coefficient, 8 by 8 coefficient, that is 64 coefficient. Okay, so U is equal to 0, 1, 2, up to 7. V is 0, 1, 2, up to 7. So this is the value of U, okay, UV as a 0, 0. Okay, f of 0, comma 0. Okay, so this is the DC value. Now, while encoding, okay, one can go like for example in this way. First we'll encode this coefficient, then we'll encode this coefficient, then we'll encode this one, and so on. So like that way we'll do the sequential scanning. Okay, now see that when you take the DCT of a 8 by 8 block whose spatial frequency is less, what will happen? You will get maximum value of low frequency and this high frequency value will be near to 0. Less high frequency value is there. After quantization it will become again 0. Okay. Now here this is the DC component. Okay, this is AC first component, second component, and this is AC 63 component. AC first component, AC1 to AC 63, and this is DC component. So in total there are 64 components, spatial frequency component. Okay, out of that, for coding this DC, okay, they are using DPCM. Okay, they are using DPCM. What is meant by DPCM? Differential pulse code modulation technique. Okay, whereas for AC they are using RLC, that is run length coding. Now what is the reason for using different coding technique for different frequencies? Okay, first we'll try to understand that one. Okay, now before that one, here it has been written like as a zigzag. You don't scan in a sequential manner. See that DC component, AC first component, second component, third component, okay, 8th component, then 9th, and so on up to 63 component. Okay, so first of all, okay, in sequential manner what we'll do, we'll code this one, then this one, and so on. Okay, but in a Jpeg it is suggested that, okay, instead of doing sequential scanning, okay, like this, okay, first row, then second row, third row, up to last row. Okay, instead of that one, scan those coefficients in zigzag manner. So like this way, okay, this one, then this one, then this one, then okay, this one, okay. So like that way it will come up to this point. Now why zigzag manner is used? Okay, I'll tell you the reason. Okay, first assume that for DC coding they are using DPCM, and for AC coefficient they are using RLC, and that too in RLC, okay, we are scanning, we are doing in zigzag manner, not in a sequential manner. Why? See, okay. Okay, first thing is that how RLC is done, run length encoding is done. So for example, I have a data like 1 1 1 1 1 1 1 1 1, okay, 2 2 2 2 2 2 2 2, and then 4 4 4 4 4 4 4 4. Okay, what is the length of this original data? 1 2 3 4 5 6 7 8 9. So there are 9 ones, then 5 2s and 4 4s. How do we do the run length encoding? Okay, how many these symbols are there? 9. Okay, okay, or this one symbol is occurring, that is special character, at how many times? 9 times. This 2 symbol is occurring at 5 times. This 4 symbol is occurring at 4 times. Okay, now what happens basically, when you take the DCT of the image, only these few AC components are dominant, okay, whereas the high frequency AC components are negligible. See, if you go in this way, sequential manner, then your run length encoding will not be effective. Run length encoding, what it does? It takes that, okay, how many times it has been occurred. Okay, so initially it will be effective. But after that, see, the whole area is of 0. So when it comes, suppose for example, from this point onward, all those pixels or all those coefficients are 0. So what you'll write? You'll code up to this point, and after that, this intensity or this coefficient value at how many times? This one. Otherwise, okay, you have to go in this way, and then it will, your coding will not be effective. Run length coding will not be effective in sequential manner. It will be more effective in zigzag manner. That's why zigzag scanning is used. Okay. Now, run length encoding here, because high frequency components are negligible, so you don't have to code for all those things. Just pass, okay, at the rate how many times it has been occurred. Okay. So your AC components will be more effectively encoded with run length encoding. Now, why differential pulse code modulation technique is used for DC coefficients? Okay. See, it is observed that, okay, now here you have these different blocks of 8 by 8. Okay, you take the DCT, two-dimensional DCT of this block, you got this 8 by 8 value. You take another two-dimensional DCT of this block, you got so like that way. For 512 by 512 image, how many 8 by 8 block will be there? 64. Sure. Okay, this is 512 by 512. Okay, this will be 256 by 256. Then 128 by 128. Okay, then 64 by 64. Then 32 by 32. Then 16 by 16, and then 8 by 8. So like that way, how many it will come? How many 8 by 8 blocks will be coming in 512 by 512 image? 4096. Okay, do the calculations. Okay, and you'll observe that. Okay, now how differential pulse code modulation technique is used? Basically, you take the difference between the consecutive thing. Okay, you take the difference between the consecutive things. Now, see that the DC value of this block and the DC value of the next block, since, okay, see that we are considering the small area. Okay, this area is more similar to this area. What will happen? The DC value of this one and this one will be same. So difference between the DC value will be less. Okay, difference between the DC value will be less. And then again, if you take the next DC value, so like that way, if you consider the only DC value of the neighboring blocks, it will be, there will be a small difference between the DC values of that one, and it will be more effectively coded with the DPCM, and that's why DPCM is used for encoding the DC values. And see, after that one, again AC component and DC component is further encoded with entropy based coding, that is Huffman coding or like that. Okay, so that you will get more and more compression ratio. Okay, so DPCM is used for DC component and run length encoding is used for AC component, and then Huffman coding technique is used for both the things, and then you'll get the finally compressed image. Okay, so this is all about baseline Jpeg 2000 Jpeg. Okay, so remaining part we'll study in our next lecture. Okay, we'll stop here. Thank you.